Good morning, everyone. I'm Rachel Blakers, a hydrologist at eWater, and welcome to our webcast. We're going to be talking about calibration for catchment modelling using the Calibration Wizard. In case you can't stay for the entire webcast, or if you have any sound issues during it, we will also email a link to the webcast recording afterwards. In today's webcast, I'm going to start with an introduction to the Calibration Wizard and some of the theory behind it. I'm going to focus on three topics. These are objective function selection, metaparameters, and optimization algorithm selection. The background to the theory is going to be followed by a live demonstration of how to use the Calibration Wizard to automatically calibrate a rainfall runoff model. Today's demonstration will be in source 3.8.20 public beta, which actually hasn't been released yet. If you are using the free public version of source, the process will be very similar, although some of the menus might appear slightly differently. Today I'm going to assume that the group is familiar with the process of creating a geographic scenario and assigning rainfall runoff models to functional units or catchments. I'm also going to assume that you're familiar with link flow routing and the concept and purpose of model calibration. The Calibration Wizard is a tool that guides the user through the process of configuring a rainfall runoff model and flow routing parameters for calibration. It's not designed for use with schematic scenarios. So for example, if you wanted to calibrate water quality parameters, you would use a different tool. When we come to running the actual calibration, we use a tool called the Calibration Runner, which we'll also cover today. The Calibration Wizard can calibrate to single or multiple gauges, and it has the ability to group parameters across several catchments, or allow them to vary individually. It provides a set of built-in objective functions, but there is also the ability to extend these objective functions via user-defined plugins. It also provides a choice of automatic optimization algorithms or manual optimization. You open the Calibration Wizard by selecting Flow Calibration Analysis from the drop-down in the source toolbar, and then clicking Configure. This brings up the first window of the Calibration Wizard. The Calibration Wizard proceeds in a step-by-step manner through 4 windows, and I'm just going to go through them briefly now, and I'm going to be focusing on some of the concepts behind what the Calibration Wizard is doing. When we come to the live demo, I'll go into more detail about which buttons you press and what all menu items mean. The first pane of the Calibration Wizard is where we choose which feature we're going to calibrate on. This can actually be a gauge or a reach, which is a less common application, but if you wanted to calibrate to observe flow at a reach, that would be possible. We then load the observed data and choose our objective function. Source provides a range of objective functions for the user to choose from, and these are available in a drop-down list. I'm not going to talk about all of these today, but you can see that most of them are various combinations of NSE, which is Nash Sutcliffe efficiency, bias penalty, and flow duration. I'm going to talk about those 3 objective functions in a little bit more detail. I'm not going to go into the equations, they're available in our documentation, but just about how you might use them and where you might use them. So the Nash Sutcliffe efficiency is probably one of the most popular statistics in hydrology. It's very sensitive to the timing of flows, and I have a slight double up in my table there, but it's not a good measure of fit to, it's very sensitive to the timing of flows, and it's also sensitive to high flows. It's not a good measure of fit to low or medium flows, and it's also not sensitive to systematic over or under prediction. The NSE ranges between 1, which means a perfect fit to your data, and minus infinity. The bias penalty measures the overall volume error. As you would expect, it's sensitive to systematic over or under prediction. but it does not measure the fit of your model to the time of the observed flows in any way. The Nash-Sutcliffe of the flow duration curves measures the fit to the distribution of flow magnitudes. So rather than just looking at over or under prediction as the bias penalty does, we're looking at the distribution of flows from low to high flows. Similarly to the bias, it does not measure the fit of the model to the timing of the observed flows. The variation on these three objective functions that I wanted to mention is to take the logarithm of the modeled and observed flows. In our charts on the right-hand side, the first one shows a flow time series in your standard y-axis. In the bottom chart, we're seeing the same flow and it transforms logarithmic y-axis. And as you can see, it emphasizes the low flows much more. So two common statistics that you might also use are the Nash-Sutcliffe of the logarithm of the flows, modeled and simulated, or the Nash-Sutcliffe of the flow duration curve of the logarithm of the flows. So both of these statistics will increase the emphasis of the objective function on low and mid-range flows. So because each of these objective functions have different aspects of the hydrograph that they are sensitive to, it's usually common to combine two or maybe even three objective functions to help the model or the optimization algorithm capture the model's ability to fit different aspects of the hydrograph. Two of the common ones would be Nash-Sutcliffe of daily flows combined with some kind of bias penalty of flow duration curve. So now we're going back into the steps of the calibration wizard. And in the second page, we will choose our warm-up and simulation periods. So warm-up and calibration periods. Source does not allow the user, Source does not allow the user to set internal model state variables. These are initialized to default values. Because of this, we need to use a warm-up period. For most hydrological models in Australia, about a year is sufficient. The calibration window is the time period over which we're actually going to be comparing the observed and the modelled flows. So during the warm-up period, the model will not compare the fit of the optimization algorithm will not compare the fit of the model to the observed flows. The third step of the calibration wizard is to choose metaparameters. And this is perhaps one of the most confusing areas or complicated areas of setting up your calibration. Metaparameters define parameter groups. And I'm just going to demonstrate how they work using a simple example of two catchments. So our two catchments that I've shown here are both forested, they're adjacent to one another, and we have observed flow at a single downstream gauge. Each of these catchments have a rainfall-runoff model assigned to them that has just three parameters called x1, x2, and x3. In this case, when we're calibrating this model, we probably want our parameters to be the same across both catchments. We have no reason to think that x1 should be different for catchment A than for catchment B. So we'd use metaparameters to achieve this. We would define, for example, a metaparameter called x1 that is linked to x1 from both of the catchments. When we vary x1, these two parameters will be changed simultaneously. The same for x2. The other point that I wanted to make was that if you don't link a parameter to a metaparameter, it won't be calibrated. That means it will retain its initial value. And you often might want to use this if you have, say, previously done a calibration and set the value of that parameter, or perhaps you have some observed data that is directly informing the value of that parameter. And in that case, you just simply don't link it to a metaparameter. Finally, in step 4 of the calibration wizard, we choose our optimization algorithm. We can select a number of algorithms from a drop-down list, which is shown here. The first approach is manual optimization, where the user manually varies metaparameter values. This is something that we won't really cover today. The second algorithm is uniform random sampling. This is available for testing purposes only. It's not suitable for calibrating most rainfall runoff models. The algorithm that you're most likely to use is the Shuffled Complex Evolution Algorithm, or SCE. This algorithm is an efficient global optimizer, so it tries to search the entire parameter space and find a globally optimal solution. Of course, because it is a global optimizer, it can be slow for large models. The second algorithm that you might use quite regularly is Rosenbrock. So this is a gradient-based search algorithm. It is very fast, but it's a local optimizer. So it might not find the globally optimal solution unless it's initialized with initial values that are close to the optimum. Another common combination that you might use is a combination of SCE and then Rosenbrock. So you use the SCE algorithm initially to do a search of the entire parameter space, and then run the Rosenbrock algorithm to speed up the convergence process for the once you think you're near an optimal solution. And that can be useful for testing. Often I'll run Rosenbrock if I'm just doing a quick test of my calibration. I want a quick convergence, because SCE does find a global solution, but it is quite slow. Now I'm going to go into our live demonstration. The example model that I've created here has two catchments, and we've already assigned a rainfall runoff model. So if I go to Edit Rainfall Runoff Models, you can see that we have 4 different types of functional units in each catchment. We've assigned the GR4J rainfall runoff model, loaded our potential evapotranspiration and rainfall data. The GR4J model has 4 main parameters, x1 through to x4. It also has these C and K parameters, which we won't cover today. These are a base flow filter that does some processing on the stream flow after it is produced by the GR4J model. We won't talk about that today, and we won't be looking to calibrate those parameters. So I'll go OK. So we have our rainfall runoff model. We've configured our catchments and all of that. The other thing that we'll need to do our calibration is to find some observed data. So here I have an example of some of the observed flow we're going to use in this tutorial, in this webcast. Source requires the observed data to be in 2 columns in a comma-separated CSV file. We can have missing values in the observed flow, and these are just left blank. So you'll see in this example, we have about 5 years of missing data at the start of the time series, and then once we get into the time series, we also have some missing values. So we'll go back to our source model. So we'll now go into the Calibration Wizard. We'll click our drop-down, change it from single analysis to flow calibration analysis, and click Configure. So in this first screen, we're going to choose the gauge that we're going to calibrate to, and that's this downstream gauge here, just above the very bottom of the network. We need to select which feature we're going to record, or which parameter we're going to record. So I'm going to select downstream flow. You can actually select upstream flow or any of those other outputs that the source model records. Once I've done that, I'm going to choose our objective function, and for this example, I'm going to use the NSE log daily and bias penalty. So our log daily is going to look at the timing and the shape of the hydrograph, focusing more on lower and medium flows. And our bias penalty is going to be sensitive to the overall volume error in our model. There are a couple of other options here. We have this weighting on NSE in combined objective. I'll just show how that works. For some of our objective functions where we have two objectives being combined, sorry, I'll get the other one. We have the opportunity to decide how much weighting we want to put on the NSE. And often you might weight it a little bit more heavily than you would your log flow duration curve, for example, depending on what the purpose of your calibration exercise is. The other option that we have on the third field is our calibration weighting. So this is if you're calibrating to two or more gauges simultaneously. For each gauge, you can assign how much weight you want to put on it in the overall objective function. That's not something that we'll be doing today either. Finally, we load our observed data. So click on the folder icon, select my time series. And it's really important to click Apply. When you've done that, you'll see that the catchments are highlighted in pink. And this means that we're going to be calibrating the parameters in every catchment upstream of that gauge that we've selected. As I'll go into when we get to the metaparameters, we can actually not calibrate all of the parameters in this upstream area. So I'll now click Next. And this brings us to the screen where we choose our warm-up and calibration windows. So in the bottom chart, what we're seeing is the observed data that I've just loaded. And I'm going to define the start of our calibration window of being just before the start of the observed data. We now need to define our warm-up period, and there's no need for a hugely long warm-up period. This top window is displaying our input data. So at the moment we're looking at rainfall, but we could also look at potential transpiration. And this just enables you to see how much data you have for your various inputs. So I'm going to drag the slider forward to about a year before the start of our calibration period, and that should be a sufficient warm-up. Now I'll click Next. If you want to, you can type in the dates exactly in these fields here. Now we come to our metaparameter definition. If I click on a catchment, you will see that in this middle window, we have a list of all the available metaparameters for that catchment. Oh, sorry, all the available parameters for that catchment. So for each functional unit, we have the 4 parameters of the GR4J model plus the C and K parameters. In the left-hand window, we can filter the parameters that we're seeing by a functional unit. So if I click on forest, we can now see that we're just seeing the parameters for the forest functional unit. We can also view the parameters for our links. So if I click on a link, we can see the parameters that we can calibrate for that link. I'm just showing you that's there. We're not going to do that today. So in this case, I want to see all functional units. I'm going to calibrate them all at the same time. And what I'm going to do is I'm going to select both catchments. So to do that, I left-click on the first catchment, and then I hold down Control and left-click with my mouse on the second catchment. Now I have all the functional units for both catchments displayed. What we could do, or what we want to do next, is decide how we're going to group all of these parameters for calibration. Obviously, if we tried to calibrate, how many are there? About 32 parameters individually, we would not get a good result. It would be too much parameter uncertainty given our available data. We only have observed flow at one downstream gauge. So what I want to do is group these parameters and say I want the x1 parameter to be the same for all functional units across both catchments. So one way to do that is to go down and select the x1 parameter for all of my catchments and functional units, and then select group. I have an opportunity to type in a suffix if I want, although I don't need to. I'm just going to call it meta for metaparameter. And you can see on the right-hand side, we've now created a metaparameter. If we click on that metaparameter and select Edit, we can then see all of the parameters that are controlled by that metaparameter, and we can also see that we have a minimum and a maximum value. This is really important. So in a lot of cases, Source will suggest sensible minimum and maximum values for your metaparameters, but not always. And it's really important that you have a look at these and make sure that they are suitable for your application. So you might have some information about your catchment that tells you that there's no way that X1 could be that high. Maybe it should only be 1,000. And you should constrain these metaparameter ranges as much as you sensibly can based on the specific properties of the catchment that you're calibrating. So I'll go OK to close that and save those changes. Now, manually creating all of those metaparameters could be actually quite time-consuming. So I'm going to delete that one and show you a different way to do it. What we can do is to use this auto group function. And what this does is it automatically groups all parameters of the same type. I'm not going to bother typing a suffix this time, I'm just going to go OK. And you can see that we've now created 5 metaparameters. And each of these 5 metaparameters relates to those 5 model parameters that we have across all of those different functional units. And you can see that also, once you assign a parameter to a metaparameter, it's no longer available in the list of parameters that you can choose from. Now, as I mentioned, we don't want to calibrate these C and K parameters. So I'm just going to click on them and delete them. So they're no longer associated with metaparameters. They will just retain whatever initial values they have in the rainfall runoff model. So now we've done the metaparameter definition. I'll click Next. I'm going to assume that my default ranges are adequate, which they are for this demonstration. And we'll go to our optimization algorithm. In this case, I'm going to use shuffled complex evolution followed by Rosenbrock. I want a reasonably quick solution for this demonstration. Let's have a look at the other options that are available in this menu. We have the number of shuffles, and that determines or influences the number of iterations that the SCE algorithm is going to run through. It's not a direct relationship between shuffles and runtime and model runs. Model runs will be much larger than the number of shuffles. We also here have number of iterations for Rosenbrock. I want this to finish quickly, so I'm going to set 20. So this wouldn't be enough shuffles and iterations normally for calibrating a model, but we do want a quick convergence for the demonstration. Now we also have the option to use values of metaparameters from your most recent calibration. This is really useful if you've already run one calibration and you've got parameter values that are quite good and you just want to tweak them a little bit. So you want to start your optimization algorithm at those parameter values that you've already defined through a previous calibration. So you can check that if you want to do that. In this case, we haven't calibrated this model anymore, so we can't check that option. We don't have any previous initial values. We also have the opportunity to manually set the seed of the optimization algorithm. So each time these algorithms run, they are initialized with a random number seed, and that influences the initial sample of the parameter space that the optimization takes. And that's what you normally want. But if you're testing your calibration, you might want to get repeatable results so that every time you run the calibration, you get exactly the same answer with the same settings, of course. In that case, you can manually set the seed of the optimization algorithm to a specific value. But normally you wouldn't do that. So we'll uncheck that. For the SCE algorithm, we have 5 parameters that the user needs to set. And Source, well, in later versions of Source, default values are suggested for these metaparameters, for the parameters of the SCE algorithm. And these defaults are based on how many metaparameters you have defined for your calibration. If in earlier versions of Source, and I think 3.7.1, you might need to have a look at these SCE parameters and manually configure them yourself based on how many metaparameters you have. If you need to do that, you can look into the documentation for further details on the SCE parameters. The final option here is to create functions for an external tool or the command line. So today we're talking about how to use the Calibration Wizard for calibrating a rainfall runoff model, but you can also calibrate source using external tools. And you do this via the command line by setting the values of functions. So checking this box will automatically create functions based on your metaparameters for use by your external calibration tool. So let's click Finish. That's all the setup we need to do for our Calibration Wizard. And I will now click Run to start the calibration. So while this is running, I'm going to open up for some questions. If you do have a question, please type it into the Go to Webinar question pane on the right. We'll also be taking questions at the end of the webinar. So do we have any questions? While users might be typing those, I'll just start to go into the display in the simulation runner. In the top chart here, what we're seeing is, in blue, the current best result of the optimization algorithm. In red is the current result. So as it's searching the parameter space, it's hopefully gradually improving the results, but it will get some quite poor fits occasionally. We'll have this option here to set the cap on the run graph. And that automatically rescales the run to a value between 0 and 1. Sorry, it rescales the graph, not the run. This is useful because often the optimization algorithm will start with some very poor values of the objective function, but typically your objective function has an optimal value of 1 as they are kind of written in source. And you might just want to look at how the optimization algorithm is doing in that range closer to the optimum, which can be difficult to see if you don't have that selected. So that will take a few more minutes. We have one question. Okay, so one user has asked for more information on GR4J. Okay, the question is about the calibration of rainfall runoff models for various land use types and soil types. Okay, and this user has used music, but would like it to link it to daily soil water content. Okay, so the GR4J model, is a conceptual rainfall runoff model. It has just 4 parameters, and these are conceptually related to some catchment characteristics, but they're not, it would be difficult to go out into the field and take a measurement and relate that directly to a GR4J parameter. If you're looking at, so you can use it to calibrate it differently for different land use types, but I think that the type of calibration that you're talking about in this question would be more suitable for a model like Sacramento, which is also a conceptual model, but it has quite a detailed representation of the soil water stores and the processes that are occurring in your catchment. Does that answer your question? We'll give that person a moment to think about it. Our next question is there any way that we can include the uncertainty of model parameterization? Also, what is the ideal number of iterations for an acceptable model calibration? I'll answer the second question first. The number of iterations depends on a lot of things. First of all, it's how many parameters you have. the more parameters, obviously, or more metaparameters, the more iterations you'll need. And it also depends on your optimization algorithm. If you have, the other important point is how good your initial guess is. So if you use initial parameter values for your optimization algorithm that are very close to the final optimum, then we're not going to need so many iterations to achieve a good convergence. The question of, so those are the two things you need to consider, but the question of actually how many iterations do you need to run is a little bit more difficult. It is actually almost a field in itself. So what source does do is this run graph does show you how the algorithm is converging. So as we can see in these last few iterations, there was a pretty small variation in the objective function value. So that gives you an idea that it is possibly starting to reach a point where it's not going to improve anymore. So one way to decide whether you've used enough iterations is just to look at, do the objective function values look like they've reached convergence? Are they no longer improving or just changing by 0.0001? The other way is to run the calibration several times with different initial values. So you've got to make sure that you don't have, you haven't set your initial random seed. If you've got enough iterations and you're using a global optimizer, you should converge to the same solution every time, or almost the same within a very, very small tolerance. So those are the two simplest methods of determining whether you've chosen enough iterations. The first part of the question include the uncertainty of the parameterization. So that is difficult. It's not the optimization algorithms that are built into source don't explicitly look at parameter uncertainty. If you wanted to do that, I would suggest using an external tool such as PEST, which has built-in tools that allow you to look at the parameter uncertainty during your calibration. You can get at it in different ways using the tools built into source, but it is a little bit more, more difficult. The next question is that by grouping the metaparameters to 4 groups, ignoring functional units, what would be the point of keeping functional units? That's a very good question. Functional units were only put in here just to show that you could. In this case, we would either not use functional units at all, so each catchment would be a single functional unit. The other approach, which you have suggested, is to group the parameters by functional unit. And you could absolutely do that. And in the calibration setup, if you filter your parameters by functional unit and then select auto group, that will enable you to do that very easily. In this case, if we don't have much information about the catchment, we only have observations at one downstream gauge. And we're using the GR4J model, which is not very strongly linked conceptually to, say, land use or soil types. I would actually say the correct approach is not to use functional units at all and just to calibrate to overall catchment flows. Our next question is, yes, source. The question is, can source be used to calibrate flow routing? It can be. Actually, so when we did the selection of the metaparameters, you remember that I clicked down and filtered for links, and that displayed the link routing parameters that we can calibrate. So we can calibrate, we have several different types of routing built into source. The most commonly used for rainfall-runoff modeling will be your Muskingum routing, and you can calibrate the parameters of the Muskingum model. I might pause questions for a moment and finish up with the results of the calibration, and then I'll come back to the rest of them. I do have one question here that said, in the example, when did Rosenbrock kick in? And I actually can't tell you in this example. You could work it out from how many iterations the SEA algorithm does based on the number of shuffles, but usually it's quite obvious because the SEA algorithm will converge very slowly, and when Rosenbrock kicks in, you'll see a sudden sharp increase in the rate of convergence. Okay, so I'll go on to just having a quick look at the results. So our calibration is finished. Normally we'd want to run it a little bit longer than what we have. In this bottom left-hand pane here, we can see each of the metaparameters that we defined and the values that the calibration algorithm has, well, the best results for those that optimize the objective functions. On the right-hand side here, we'll actually have a list of our current optimums and previous optimums, and this result is really useful if you're doing a manual calibration and manually editing the calibration, the metaparameter values. You'll see the results of each of your successive runs listed down the right-hand side here, so you can compare your two previous results. If we click on the second tab, we can look at the charts of our observed and simulated flow. So I'll click View. So what this chart is showing, in red, we have our simulated flow, and that is shown for both the warm-up and the calibration period. And we also have our observed flow in blue. We can click on the second tab and see the table of values. The observed flow has a lot of NAs at the start for missing data. And on the third tab, we can see statistics. So these include the objective function that we selected for this calibration, which was the NSE log daily and bias penalty, but it also shows all the other objective functions that we have available in the calibration runner. So you can compare not just to the one you're optimizing to, but also validate against other measures. If we go back to a chart, we might want to look at it on a logarithmic axis, which is more appropriate given that's what we're calibrating to. And that will show us how our model is fitting the observed data for those low flows a little bit more clearly. So you have several different chart types that you can select there. For example, our cumulative, I'll have to turn off our logarithmic axis. And there we can look at the cumulative flow volumes of the two time series. So I'll close those results. That concludes our demonstration of the Calibration Wizard. And I'll now go back to more questions. And our first one is, what is an acceptable best result range? What is the lowest best value that you would accept? That's another difficult question, and it's a very grey area. If you're using the Nash-Sutcliffe efficiency, a value of 0 means that your model is performing as well as taking the mean of the data. Now, so that would suggest that if your model, with all of its parameters, can't perform better than just taking the average of the data as a prediction of what's going to happen next, that's not good enough. What is an acceptable value really depends on the purpose of your model and the quality of your data. So if you're doing short range forecasting, you would want a high degree of accuracy probably. So NSE of above 0.8 or 0.9. Often I'm quite pleased in my hydrological calibrations if I get a value above 0.6. So that is a really difficult question, and there isn't a single answer to it, and you have to look at your models visually, have a look at how your model is fitting the observed data, and whether, not just based on your statistics, but whether you think it is adequately capturing the processes that are occurring and the processes that you're interested in. Just, yeah, let me know if you want more to discuss that further. Can Source be used to automatically calibrate the Sacramento model? The answer is yes. Source has built into it, I think, about 8 or 9 different rainfall runoff models. They include JR for J, Sacramento, IH Acres, SMA, I can't remember them all, so the answer to that is yes. The next question is, what is your recommendation on using distributed hydrological models for Australian catchments? Yes, so you're talking about spatially distributed models. I'm pausing for a moment. It really depends on how much data you have available, and often you don't have very much. Look, I would say it's going to be a much larger investment in time and resources to set up your spatially distributed model. You're going to have a lot of parameters that you need to calibrate, and those parameters are going to have enormous uncertainty because almost certainly you won't have enough observed data to adequately define your parameters. So then you're going to definitely need to use, if you're using automatic calibration, you're going to need to use a sophisticated calibration approach, for example, like PEST, where you use regularization conditions to help constrain your parameter values. So my answer is I wouldn't launch into it initially, but if you do an initial calibration, say using your conceptual model, and for some reason it's either not adequate for your purposes or it's not adequately capturing the processes, then consider moving to a spatially distributed model. But there is a lot more investment in there. We are starting to run, so we have if you could discuss that some more, this follow-up question. The lowest best value question. Okay, so a little bit more information about the lowest best value. So I personally, if I see a Nash-Sutcliffe score of below 0.5, I would consider that my model is probably not really adequate. I would not have much confidence about the predictive performance. If you could follow up with a little bit more information about exactly what aspects of the lowest best score you wanted me to elaborate on, that would be helpful. For the bias penalty, for example, or the absolute error in the bias, because that will also affect your overall combined score, that's actually a little bit easier to determine, because if you're, say, using your model for some kind of policy purpose, you might say, know that volume errors of more than 10% are unacceptable. So if your volume errors were 15%, you'd say this is not an acceptable result. You could try to then either change your model, improve your model, gather more data. In some cases, the reality is that the information available simply isn't good enough to build a model that will have a better performance than what you're getting. So whether the model is fit for purpose does depend on your specific objectives. For some applications, not so much in hydrology, but an error of more than 1% in the volume will be unacceptable. So that's why it's such a difficult question to answer, because it really does depend what you're using the model for. If you're interested in flood forecasting, for example, it might be really important to get the high flows correct, but if the low flows are out by 100%, you really don't care, as long as the model predicts your high flows accurately. So I'm sorry, I'm not sure if I've really helped with that one, but if you want to follow up more. So we have another question. Is the Calibration Wizard helping in calibrating lumped models? To follow on, how to include one of these models in the wizard? Okay, so I can demonstrate that quickly. So the question is how to calibrate one of the other models using the Calibration Wizard. That's actually very easy. We just go to our Edit Rainfall-Runoff Models, and then all we do is we select our model type, and select the model that we would prefer. So let's choose Sacramento. I'm going to change, oopsie, I'm sorry about that. I've broken something. So what you do, I am running on the public beta that hasn't yet been released, so we have a little glitch there. What you do is I'll leave that for the moment. You change your model to your preferred model, say Sacramento, and then when you go into the Calibration Wizard and select on your metaparameters, instead of seeing the parameters for the G alpha J model, you'll see the parameters for your selected rainfall runoff model. If you have more than one rainfall runoff model selected, you'll see the parameters for both. Sorry, I'm moving back to the presentation. Are there more questions? So the next question is, can we control the random start of the optimization algorithm when we use quasi-Newton or PEST? The answer is yes, because in those cases, the random start of the optimization will be determined by PEST or whatever optimization tool you're using. So that's actually something that Source doesn't need to have any input on at all. So you'll set that within PEST. The next question is, can the Calibration Wizard be used to optimize large river basin models like IQQM SWOT? So I'm not quite sure what aspect of that of large river basin models you mean. I think the answer is yes. So we can use the Calibration Wizard to calibrate as many models as we like. The only limitation, of course, is that the bigger it gets, the slower the runtime. So if the only limitation is runtime. Let me know if that answers your question. Or unless you meant, can we use the Calibration Wizard with IQQM, which we couldn't. Yeah, but let me know if you want to follow up on that question. The next question is, can you calibrate to a subset of the flow duration curve to focus on extreme floods, for example? That's a good question. To do that, you would probably need to write your own user-defined objective function as a plugin. And that came up recently, so I think the answer is yes, but you would need to write your own plugin because it's not one of the built-in functions. Then the next question is, does G alpha J consider the groundwater surface water interaction, or how does G alpha J consider the groundwater base flow? Okay, so the G alpha J model that I used today doesn't consider surface groundwater interactions. If you want to, we do have a groundwater model included in Source, and you could link that with your rainfall runoff model. G alpha J by default produces a single time series of stream flow. Now you remember those two parameters called C and K that I avoided? Those two parameters define a what's called a base flow filter, and they enable you to, as a post-processing step, provide a filter that separates your stream flow out into quick flow and base flow. But if you're particularly interested in base flow and surface groundwater interactions, I'd suggest using one of the other models that are available in Source rather than G alpha J. The next question is, can you briefly describe the calibration process for a small river system? Say, one calibrated inflow and one reach. Well, I think what I've demonstrated today has essentially demonstrated that process, except for the calibration of the reach. Source is typically run on a daily time step, and if you have a small river basin, probably the rainfall event and flow that results is going to occur within 1 day. So you're not going to have an observable lag in your stream flow compared to your rainfall. So for a small river basin, you might not actually need to include flow routing as a separate component of your model. If it is a slightly larger basin and it takes, say, a couple of days for your stream flow to reach the stream after a rainfall event, then the typical process would be to perhaps do an initial analysis of your rainfall and stream flow to get an idea of what the lags are, and then the routing parameters are often quite insensitive, which is why you want to do that initial analysis. And I often prefer to set those values from my analysis of the hydrograph and then just calibrate the rainfall runoff model based on those routing parameters, because there will be an interaction between the two. If you change your routing parameters, it's going to influence the optimal rainfall runoff parameters. Or you could calibrate them both concurrently. So when we did our metaparameter selection, you'd select the catchments, which use metaparameters, then you'd filter for your link routing parameters and create some metaparameters for those, and the model would calibrate them both at the same time. So we have time for just one more question, and that is, will there be another webinar on the Calibration Wizard going into some of the more complex areas of the SEA algorithm and a full overview of the best calibration approach? We don't have one planned at the moment, but I will talk about further support at the end of the webinar, so I'll answer your question indirectly shortly. Email support@ewater.org.au to attend our upcoming course. And I will just wrap up. Sorry, I was just going to, we'll send another email to everyone who asked a question that we didn't get a chance to answer. So I'll just wrap up with the key points from this presentation, and then the information about further training. So choose your objective functions and your optimization algorithms carefully. Your objective functions need to reflect the purpose of your model, and your optimization algorithms have to consider the dimensionality of your problem, that is how many metaparameters you have, and how good your initial guesses are. A warm-up period must be used because you can't set those initial state variables for your rainfall runoff model. And use metaparameters to group your parameters, and it's really important to consider your metaparameter ranges because and constrain those to something sensible for your particular catchment. So topics that we haven't gone into today, like how you create geographic scenarios, configuring and calibrating your links, and external calibration and optimization tools, such as Insight and our command line running. If you want more information on those, I'll suggest two sources. First of all, if you have a support and maintenance agreement, or if you're a member of one of our partner projects, you can contact us at support@ewater.org.au. Otherwise, we have a course coming up on the 4th and 5th of May that covers building a calibrated rainfall runoff model using eWater source and the Calibration Wizard. If you're interested in that, you can register online, and I have the link on the screen there. Limited places still available for that course. So I'll step back. So that concludes the webinar today. We will follow up via email the questions that I wasn't able to answer. And thank you very much for attending.